Okay, so this is a Hamilton circuit problem. Essentially, we have a set of vertices and weights on the edges that connect them, and we want to find a path that starts and ends at a particular vertex, making sure that we hit each of the other vertices exactly once. And we have a few different methods or algorithms for doing that. Two that we're looking at here, the nearest neighbor and the best edge. So we see this table, and what this does is gives us the distance in between any two vertices in terms of minutes. So, for example, to go from Esther's place to Carlos' place, it would take 7 minutes, or from Carlos's place to Esther's place. To go from David's house to Bobby's house, or vice versa, that would take 6 minutes. So we can draw these out on a graph where the vertices are the different homes and the edges are the paths in between them, and we have them labeled by how many minutes it would take to travel that particular path. So since we need to start and end at home, using the nearest neighbor algorithm, we want to start our actual path, start drawing our path from home also. That's not necessarily the case in best edge. But in home, starting from home, we want to find the person who lives closest to us, and in this case it would be Esther, and you can see that in the table. You can also see that down here. Let's go ahead and label that. This would be nearest neighbor, so let's label that red. Okay, so we've now traveled from home and we're sitting at Esther's house, and now we're asking who's the nearest neighbor from here. A couple rules though. We want to make sure that we don't complete a cycle until we've visited everyone's home. We don't want any cycles in our path until we've visited everyone and we're going home. Then we'll complete a cycle. We also want to make sure that we don't visit a vertex more than twice. We're just visiting them exactly what we need to. Once on the way in, once on the way out. So now looking at Esther's, we could go to B. That would be 12 minutes. Carlos's house would be 7, but David's is only 2 minutes. That's the closest one to us, and so we want to go ahead and take that path. So we've gone from home to Esther's to David's. Notice we could not go back home right now. Even if that was the shortest path, we don't want to complete any cycles until we visited everyone. That's a pretty important point there. Okay, so we could now go, we can't go home, but we could go to Bobby's house. That would take 6 minutes, or Carlos's house would take 5 minutes. Again, we're choosing the nearest neighbor, whatever number is lowest. It's not visually, it's not like an XY graph where C it looks closer to D. What we're really paying attention to is this number here. So since this is the lowest number, we're going to grab that. Now we're at Carlos. So notice, not only can we not go home, although that's the shortest path here, right? That 3 is shorter than the 7 and the 4 that we could choose from here. But that would create a cycle. And in fact, even doing that 7 would also create a cycle here. So we can't choose that 7 or that 3, meaning that we need to choose this 4 here. And from this point, we visited all the vertices here, so we really don't have any choice. We just have to go back home. Notice it is kind of a long way home here in terms of the minutes, but we don't have a choice at this point, and now we've completed our circuit. So if we're going to write that out, we're starting with H, would be our starting point, and then we went to E, then D, then C, then B, then H was the path that we followed along the nearest neighbor. And we can go ahead and total that distance too. It'd be 1 minute, 2 minutes, 5, 4, 10. If you add all those numbers up, you would get 22 minutes. So that's nearest neighbor. Now let's look at best edge. So the difference here with best edge is we will create a path that starts from home eventually, but we don't have to select one immediately. Now in this case, the best edge does happen to be connected to home, but let's say that this one was down here instead. We would still choose it even if it wasn't connected at home, because after we create our entire path, we can just write the labels on that path so that we're starting and ending at the home point, since it's just a big cycle anyway. So you're choosing the best edge right here, even if it's not attached to home or your starting point. In this case, however, the one is, so we want to go ahead and choose that. And we'll do green here for best edge. And now we want the next best edge. However, again, we're not going to allow ourselves to create a cycle until we've included all of the vertices, just as in nearest neighbor. That part's the same. The difference is we don't have to be connected here. We also want to make sure that we don't have more than two edges selected for a specific vertex, because that means we'd have to visit the vertex more than once, and it would end up costing us more. So looking over the rest of the options here, the lowest one would be the 2. Again, it just so happens to be connected to the 1, but we don't have to choose. If the 2 was over here instead and this was a 4 or something, we would still choose the 2. So it's a different process than the nearest neighbor. So I'm going to go ahead and choose the lowest one here, which is the 2. And now notice that the next one that we have available would be the 3, would be the next lowest of the ones we haven't chosen yet. And the 3 is not attached to the 2 that we just chose. That's okay. In the nearest neighbor, you're always looking at the ones that are attached to your current point. Not so in best edge. This best edge does happen to be attached to our starting point, but it wouldn't have to be. Again, that 3 could be down here. If that was the lowest number remaining, we would choose it even if it's not connected to the other edges we've chosen so far. So I'm going to go ahead and choose this 3. Okay, and again, I'm looking for the lowest available edge. However, I don't want to create a cycle until I've included everyone. And I also want to make sure I don't have more than 2 edges going to a specific place. So home is already at its max. It's got its two edges there, and so does Esther's house. So I'm definitely not going to be getting any edge that connects to Esther's or home right now. But looking around at my available options, I see that 4 would be the lowest. It's not going to create any cycles. It will mean 2 edges coming out of C, which is fine. I can have up to 2 edges. So I'm going to go ahead and choose that. And that really doesn't leave us with much choice now, because Esther's already got 2 edges, Home's already got 2 edges, Carlos already has 2 edges. The only thing left to do is travel this edge here between Bobby and David's house to go ahead and complete. This time we can complete a cycle because we've included everyone now. And so now we have our best edge path. Now that we have it, we can go ahead and write it. So here we do start from home. Notice that we have the cycle. Even if this wasn't the first one we laid, now we can make sure that our path does start from home. So we put an H. But here we have a choice. We could either go E or C as we're following this green path. Does not matter at all. It's going to be the same total distance. For anything that we're doing here, it's not going to matter. So let's just go E. And then we're just following the path around, following the green path. So we'd go D, B, C, and back home. D, B, C, and back home. And then just as we did with the nearest neighbor, we can calculate that total distance. So we have 1 here. Now we're at 3. Plus 6 is 9. 4 is 13. And 3 is 16. So that total path was 16 minutes. And again, notice that it would have been fine to go backwards on that same path, and we still would have gotten 16 minutes. So the nearest neighbor algorithm gave us a path that was 22 minutes, and the best edge gave us a path that was 16 minutes. Obviously, if you had to choose between the two of those, the best edge would be better. So why don't we always just go with the best edge? Well, sometimes the nearest neighbor gives us a better path, and sometimes the best edge gives us a better path. So it's nice to have two approximations. And it's very possible that there's a third path that's even better than both of these. So keep in mind that it's an unsolved problem unless we want to do what's called brute force and calculate all the possible routes through, or something very, very similar to that. We won't know that we have the best path, but these nearest neighbor and best edge do give us fairly good paths through, and you should know how to follow step by step each of these two algorithms.